All right, guys, and moving on into the second half of 14.2, now's when we're going to start actually solving trigonometric equations. So notice here, guys, that in these problems, we're giving a limited interval right here, that we're looking for x values that are in between 0 and 2 pi. And also notice it's not a coincidence, I included the or equals to sign there, but not there. And what that means is that it is okay for x to equal 0, but it's not okay for x to equal 2 pi. X has to be less than that angle right there. And what that little stipulation here does, everybody, is it basically takes what could be a really big mess with a really high number of solutions and trims that down to something a little bit more manageable for us here. So let's take a look at our first trigonometric equation. 2 sine of x minus 1 is equal to 0. Well, you guys have been solving equations for years now, and every time we do it, the overall goal is the same. Get x by itself. So that your answer might be something like variable equals number, constant, and that's when you know you're done, and then you can check your answer by plugging that value back in for x and making sure that you get a true statement. I'm pretty sure 8 is not going to work here, but regardless, that's what we're shooting for here. So, find your variable, figure out what's being done to it, and undo everything. Here's our variable right here, x. The first thing happening is that they're taking the sine of x. Then that's getting multiplied by 2, and then we're subtracting 1 from that. So the first thing we're going to do is get rid of that minus 1 by adding 1 on both sides. And we're going to have now a 2 sine of x is equal to 1. And then from there, let's get rid of the 2 by dividing both sides by 2. And that'll leave us with the sine of x is equal to 1/2. And from there, what we really want to do is take the inverse sine of both sides. And I didn't leave myself much room there. Okay, inverse sine and sine cancel each other out, and we're going to get x equals. And now what we need to evaluate is the inverse sine of 1/2. So back to what I was just doing at the end of the previous video then, inverse sine of 1/2. Well, sine is y, so we want to know where on this unit circle is our y coordinate equal to 1/2. We're going to graph that line right there, guys, which again, because it is y equals a constant, is a horizontal line. And where is y equals 1/2? Here's 0. Here's 1, 1/2 is directly in between them. So we're looking at this horizontal line right there, y equals 1/2, which crosses the unit circle twice. Once, I should have started here, once right here on the right and again here on the left. And we are looking for all solutions in one complete revolution of the unit circle, meaning starting here at 0, and going all the way around until we get back to where we started. So our first solution, not that the order really matters, is right there. And what angle is that? 30 degrees north of 0 there, guys. That is the angle pi over 6. Notice, since the interval they gave us was written in radians, our answer should be in radians as well. Or a second solution now would be x equals, and now we'd be talking about this angle right here, which is 30 degrees shy of a half circle. That is going to be 5 pi over 6. And those, you guys, are the two solutions here to this particular equation. Now, how can I check that? Just like I check my answer to any equation. I can plug it back into the original statement and make sure we get a true statement. So let's try that real quick. 2 sine of x minus 1 is equal to 0, so let's try this. And yes, my calculator is in radians. So 2 times the sine of, the first angle we came up with was pi over 6. Gotcha. Let me get rid of that parenthesis. And then there was a minus 1 at the end of all that, and we should end up with 0. And we did. Guys, if you're doing this on your 84, make sure your mode is in radians. If you're in degrees and you type this in, it will not work out. The second one was 2 sine of, and we believe our second solution was 5 pi over 6. And then we'll subtract 1 from that as well. And there you go, we got 0 yet again. So that proves now that our two solutions that we came up with actually work. It doesn't actually guarantee that they're the only two numbers that work, but that is very often the case with a problem like this, that you're going to end up with two solutions. All right, let's move on to another one. The cosine of x plus the square root of 2 is equal to a negative cosine of x. Okay, this one's a little weird because we've got variable terms on both sides. So to fix that, I'm going to add this cosine of x to the right and also to the left. And at the same time, I don't like where that root 2 is. I'm going to move that to the other side by subtracting a root 2. So these terms are going to cancel. Those are going to cancel. And that's going to leave us with cosine of x plus cosine of x. Well, anything plus itself is 2 times whatever that common term is. 2 cosine of x is equal to, and then we have a negative root 2. All right, next thing, we're going to have to divide both sides by 2 here to isolate the cosine of x. So cosine of x is, all right, it's ugly, but I recognize this ugly number, negative root 2 over 2. And now we'll get rid of the cosine by doing an inverse cosine on both sides. These cancel out, and we're going to get x equals. All right, guys, and this is what we now need to graph. Remember, cosine is x, so we need to graph the line x equals negative root 2 over 2. Now, it would benefit us to probably know what that is as a decimal. So let me go to my calculator and type in negative square root of 2 divided by 2. And asking for that as a decimal, I get negative 0.707. All right, let me jot that down. Negative 0.707. Now, since it's x equals, this right here is a vertical line, one that's running this way, and its x-intercept is negative 0.707. All right, guys, where does that go? Right here, we're at x equals 0. All the way over here is x equals negative 1. Right in between them is x equals negative 1/2. And right here, guys, the second of these 3 lines here, moving away from the origin, is what we want. That's negative 0.707. You'll notice, well, let me get to that in a minute. I'm going to go ahead and draw this line right here, the vertical line, the only one, with an x-intercept of negative 0.707 or negative root 2 over 2. So where does that green line cross the unit circle? Once right here, everybody, where we have a 45, 45, 90 triangle drawn within the second quadrant. That angle is going to be 3 pi over 4. Or we have a second solution now right here, which also creates a 45, 45, 90 triangle down in the third quadrant. This angle here is 5 pi over 4. And there's the 2 solutions that we've come up with here to this particular equation. Now, the point I wanted to make a second ago, if you thought I was just kind of guessing that this value right here was 1/2 and this one was 0.707, come on, Mr. Fontana, how can you tell that's 0.707 instead of 0.75? Well, I get where you're coming from, but remember, up from that point, we located this dot right here, which created a 45, 45, 90 triangle. And with what we know about 45, 45, 90s, we know that the hypotenuse should have been 1 because we're on a unit circle with a radius of 1. And what I'm hoping you guys knew is that this leg down here is negative root 2 over 2. So that's the actual value right there. This is just the approximate decimal. In the previous problem, we were dealing with 1/2. And I guess I didn't draw my triangles here, but at the point where I thought my solution was, if I draw the altitude and the radius, here's a 30, 60, 90 triangle with a hypotenuse of 1 and a short leg equal to 1/2. So that's actually where those dotted lines in the diagram come from, guys. We're kind of doing this in that order, not the opposite way that people sometimes think. Okay, this problem is tough for 2 reasons. Number one, we haven't done tangent yet, which is a little bit weirder than sine and cosine. And second of all, we have squared going on here. But we're going to handle this the same way kind of as the last one. You want all of your trigonometric terms on the same side of the equation. So I'm going to add a tangent squared of x on the right, and we'll do the same thing on the left. And I'm going to get rid of that 4 as well, guys. So I'm going to add a 4 to the left and 1 to the right. So let me draw a little line right here. These terms are going to cancel out. So will those two. And that's going to get us 3 tangent squared of x plus 1 tangent squared of x. That is a 4 tangent squared of x is equal to 4. Next move, let's get rid of that coefficient. We'll divide both sides by 4 here, and we will get tangent squared of x is equal to 1. And now the fun part. To get rid of the square, remember guys that even though we write it as tangent squared of x, what that really means is tangent of x, and then the whole quantity is squared. We're now going to take the square root of the left and the square root of the right. So on the left side, the square and the square root cancel, and we're just going to get tangent of x. And on the right side, you got to be careful here, guys. Everybody's going to tell me that the square root of 1 is 1, which is true. But there's also another one. This could actually be negative 1 as well. So the tangent of x is equal to either positive or negative 1. Last step now. To get rid of the tangent, we would do an inverse tangent of the left, and again, I didn't leave myself much room here, an inverse tangent of the right. So we'd end up now with x is equal to, all right, and now it's time for the green lines here. We need inverse tangent of 1. Well, remember, guys, the definition of tangent is y over x. We need to know where that is equal to 1. So with a tangent problem now, you want to multiply both sides of the equation by x so that these terms cancel, and you get the line y equals x. That's a diagonal line with a y-intercept of 0 and a slope of positive 1, 45 degrees. So I'm looking at a line here, I should say the line that does this. And how many solutions did I get here? One right there and one right there. But wait, there's more. Back to this, guys. We also have to be looking at the value of inverse tangent of negative 1. So in that case, it would have been y over x is equal to negative 1. And when we multiply both sides by x now, we're going to get y equals, I'm sorry, guys, I wrote that wrong, even though I did it right. That should have been y equals x. Here now, negative 1 times x, y is going to equal negative x. So that's another line with a y-intercept of 0, but now your slope is negative 1. So we're going here into the second and the fourth quadrants. So that line, the second one that we drew, also has 2 points of intersection, one right here and one right here. So let's take a look at those 4 blue dots, everybody. Those are our solutions. The first one right over here is x equals pi over 4. Or the next one right over here, x is equal to 3 pi over 4. Or a third one right there, x is equal to 5 pi over 4. Or our fourth and final solution between 0 and 2 pi, x is equal to 7 pi over 4. So I said a while ago that most of these trigonometric equations have 2 solutions, which is generally true, but because this one had tangent squared in it, we actually ended up with 4. Now, what I'm going to do next is dive into this little variation on the problems we were just working on. Now, depending on what year it is that you guys are watching this and who your Algebra 2 teacher is, they may or may not give you this set of directions. What we're going to do now is not just limit our solutions to one revolution on the unit circle from 0 to 2 pi like we were doing right here when we talked about that, guys. Now, we're going to start talking about finding a general solution. In a weird way, we're going to ask you guys to list every possible answer to this equation. Now, if this is not something you guys are covering this year, ignore those directions and just keep doing these problems the same way we were. I still think there's some valuable practice in these last 3. So let's take a look at what's going on here, guys. 2 sine of x plus the square root of 3 equals 0. First move, we're going to subtract the square root of 3 from both sides. And that is going to give us 2 sine of x is equal to negative root 3. From there, we'll divide out a 2 on both sides and get sine of x is equal to, leave some space, negative root 3 over 2. And lastly, how do we get rid of a sine? With inverse sine. And we're going to do that to the left and to the right. And look at me, I remembered to leave space that time. Those two cancel out, and we're going to get x is equal to, all right, inverse sine of negative root 3 over 2. So remember, everybody, sine is y. So we want to know where on this unit circle does y equal negative root 3 over 2. And as we said a while ago, that is negative 0.8 0.866. Now, y equals is always a horizontal line, and negative 0.866, well, let's think about that, guys. There is 0. Down here is negative 1. Negative 0.866 is about as close as you can get to that negative 1. It's right here. So there is the horizontal line that we're going to draw, and this one crossed the unit circle twice. Once right here and once right over here. Now, this solution, we actually saw this one earlier in this section right here, is, if I'm not mistaken, 4 pi over 3. This solution right here, I'm going to write this underneath this now, is 5 pi over 3. But here's where it gets weird, guys. What we're going to do, let me try to explain this here. At the end of our first solution, x is equal to 4 pi over 3, we're going to put plus. And what we're going to put is something weird here, guys. 2 pi multiplied by n. And we have to specify what that means here, where n is any integer. Now here's what that means. If n were a nice easy integer like 1, 2 pi times 1 would be 2 pi. And what we're saying is there's another solution. We found 2, but there's a third one at 4 pi over 3 right here, plus another 2 pi, which is another complete revolution to take you around that unit circle there. So I believe that would be 10 pi over 3. Then, if n were equal to 2, that would give you yet another solution at another complete revolution around the circle. Because of coterminal angles, this can keep happening over and over and over again. So we add this 2 pi n at the end of the first specific solution to just say, hey, this can happen an infinite number of times where n could be any integer, a positive or negative whole number. And that's basically how we handle complete or general solutions. I'm going to do the same thing down here with 5 pi over 3 plus 2 pi n. And that right there, guys, I know it looks weird, represents an infinite number of solutions, because in each case, there's an infinite number of values that you can put in there for n. Kind of a weird one. Let me show you what I mean by that real quick. Okay, so I just said that one of my solutions here, let me write this, was going to be 5 pi divided by 3. So 5 pi over 3 plus 2 pi, and multiplying that by an n value. I'm going to pick a weird integer like negative 13. Okay, that gets me negative 73 pi over 3, which according to what I've written down is a solution to this original equation. So now I'm going to try typing in that original equation that I have in black right here with that goofy number I just came up with, and I better get 0. So 2 sine of x plus root 3. All right, guys, this is going to be 2 times the sine of, and the angle we just came up with was negative 73 pi divided by 3. So, okay, that is 2 sine of x, and then there should be a plus root 3 at the end of all that. So plus the square root of 3, and if we've done this right, we should end up with 0. And we did. So I certainly wouldn't thought of it that way, but negative 73 pi over 3 is a solution to this equation because I put it back into the original equation and got a true statement. It did give me 0 on the left-hand side. So that's just kind of illustrating the point here that if you're not limiting yourself to one revolution from 0 right here all the way to 2 pi, but if you keep going around and around and around and around, you can be here all day, you can actually come up with an infinite number of solutions to these equations, which kind of makes your head hurt. I get it, but that's how we handle it, guys, just plus a 2 pi n. Okay, I have 2 more examples to do with you. This one will work, a little bit like the last one, but you're not going to like something that happens here. For the first time today, we're seeing a trigonometric equation that has a trig ratio squared right here, but it also has one that's not squared. It also has one that's just taken to the first power. So we did this example here a little while ago, but both of our terms were tangent squared. This one here is tougher, and you guys are going to love this. What we have here, guys, is a trinomial expression on the left side. There's term number 1, here's term number 2, there's term number 3, and it's set equal to 0. And if you look at those three terms, we have a squared term, which makes it quadratic, a linear term, and then a constant. What this is, you guys, you ready for this? Is a quadratic trigonometric equation. And how did we learn to solve quadratic equations back in chapter 4? By factoring with reverse FOIL. The process is exactly the same, it just gets a little bit weirder here. Let me show you what I mean. I need something to go here and something to go here that multiply together to make 2 cosine squared of x. Well, if that 2 wasn't there and it was just cosine squared of x, we would just put cosine of x times cosine of x. But with a 2 there, I also need 2 coefficients that multiply to 2. One of them is going to be 2. So 2 cosine of x is going to go here, and the other one is 1 cosine of x. And if you guys think about this, hopefully you're with me here, 2 cosine of x times cosine of x gets you 2 cosine squared of x. Okay, cool. Now, going back to chapter 4, I look at this sign right here first. And since that sign is a negative, that tells me that these two signs down below here are going to be opposite. One is a plus and one is a minus. And I don't know which one is which. I'm going to just go in order here, plus and then minus. But I've got to test this and find out if I guessed right, and it's a 50-50 chance that I guessed wrong. I might need to come back and fix it. Now, I just need 2 numbers that multiply together to make 1. Well, that's pretty easy. The only options are 1 and 1. And now, guys, to find out if we factored this right, we'd have to check ourselves with FOIL. First product, this times this is 2, and then cosine of x times cosine of x is cosine squared of x. The outer product here is minus 2 cosine of x. The inner product right here is plus cosine of x, and the last product here and here, positive 1 times negative 1 is negative 1. So now the question for you guys is, does this expression right here simplify to equal this? And when you combine these two like terms in the middle, yes it does. We guessed right here, guys. We got that minus cosine of x in the center. So factoring is all about guessing and checking and then making adjustments if you guessed wrong, which very often happens, but in this one it worked out fine for us. Now, might be a little hard to remember, what do we do after we have factored a quadratic expression? You take each factor, this factor here, and this factor here, and you set each one of them equal to 0, and then solve. So here we're going to get cosine of x minus 1 equals 0. And this basically becomes 2 separate problems now. Let's work on the left. I'm going to subtract a 1 on both sides and get 2 cosine of x is equal to negative 1. We'll divide by 2 and get cosine of x is equal to negative 1/2. And then we'll undo the cosine with an inverse cosine. X is equal to the inverse cosine of negative 1/2. Okay, I guess while I'm at it, let's go ahead right here. So, inverse cosine, we're talking about x, guys. So we want to know, where is x equal to negative 1/2 on this graph? That's a vertical line. Here is 0. Here is x equals negative 1. Negative 1/2 is right in between them. So here is the line, x equals negative 1/2, and it crosses the unit circle twice. Right here and right here. That first point right there, guys, is x equals, that's going to be 2 pi over 3. And since we're finding general solutions, I'm going to have to add something to that. I'll go ahead and do it now. 2 times pi times n. The second solution then comes right here. We're down in the third quadrant now. That is going to be 4 pi over 3, and again we'll add a 2 pi n at the end of that. Halfway home. Now, on the right side, let's start solving this equation. We'll add 1 to both sides and get cosine of x is equal to 1, and get x is equal to the inverse cosine of 1. So now we want to know here, everybody, where on this line is, on the circle, is x equal to 1. That, again, is a vertical line, and the only spot here where your x-coordinate is 1 is right out here all the way on the right. That line is actually tangent to this circle right there, so the only solution we got is right there, everybody, where we're going to get x is equal to 0 degrees or 0 radians, and again, we would add 2 pi n to all of that. So I would say, guys, for what we're doing right now and at this level, these are your solutions right here. Now, if we wanted to get really fancy, it looks like the spacing of these three solutions is actually even. You're going, what, 120 degrees or 2 pi over 3, and again. So if you wanted to be really efficient, you could have written this out as x is equal to 0, your first solution, plus, and then it would be 2 pi over 3 times n. This one statement, and I guess you don't need that, this one statement here in red covers everything in blue, but nobody cares. We're not getting that fancy right now. What we had in blue is just fine. All right, guys, last example. Let's take it home. This one might actually be easier than the last one. Okay, let's get our tangent terms together. So I'm going to bring this guy over here. Adding that 2 tangent of x to the tangent of x is going to give us 3 tangent of x equals root 3. We'll divide by 3 on both sides and get tangent of x is equal to root 3 over 3. And then when we take the inverse tangent now, we're going to get x is equal to the inverse tangent of root 3 over 3. And I haven't given you one like this just yet. So what we need to do is graph a line on top of this unit circle, and with tangent, remember that tangent is the value of the ratio of y over x. We want that to equal the square root of 3 over 3. And if you multiply both sides by x now, you're going to get y is equal to the square root of 3 over 3 times x. Now, because these tangent equations contain both an x and a y, these are diagonal lines. Their y-intercept is always 0, so this line needs to cross through the origin right there. But now, I need to know which of the dotted lines that pass through the origin has this slope of root 3 over 3. Well, what I'm hoping you guys can tell me is this. The square root of 3 over 3, is it equal to 1? Is it greater than 1, or is it less than 1? I'm hoping you guys know that the numerator, the square root of 3, is smaller than 3 itself. That means that the value of this fraction is less than 1. Now, why is that significant? Because this line right here, you guys, this might confuse you if you put this in your notes, so you might just want to watch this. This line right here, going through at a 45-degree angle, has a slope equal to 1. Therefore, since our slope has to be less than 1, it would have to be this line right here, guys. That's the only line here passing through the origin with a slope of positive root 3 over 3. It's got to be smaller than 1. This line right here is steeper than that 45-degree line. It's got a slope that's actually greater than 1. So the only two solutions I'm looking at are this one right here and this one right here. So here we would say that x is equal to, this solution right there, everybody, is pi over 6. And, okay, here's what's a little tricky. I know this year we haven't really talked about that. The period of a tangent graph, which we skipped this year, is equal to just plain pi. With sine and cosine, it was 2 pi, and that's why we stuck that on the end here. So really, this is pi over 6 plus pi times n, and that actually gets you this solution right over here, because this distance between those two is equal to pi radians. That's half of a circle. So actually, this one little statement right here, everybody, is sufficient for your solution. You don't need a 2 pi n here, because the period of tangent is just pi rather than 2 pi. Okay, all right. Guys, 14.2 is a tough section. Even if you wrote down and understood everything we did here, you still need to dive in and get some practice before you really start to understand that on your own. All right, guys, good luck with section 14.2. Try that homework and let us know when you guys have some questions for us.